Hello, nice to meet you. I'm Master Haejun from Samsung Research, and our team has been working on GAUS, our own large language model. And recently, we have paid special attention to knowledge distillation, KD technology. So today, I want to talk about the areas that we have reviewed for various knowledge distribution technologies, and then what kind of strategy can enhance and maximize the performance of your models by installing KD technologies. This is my content. I will first talk about what knowledge distillation is and what needs to be distilled and how we should select the source models and data, and what is the most efficient way to use the resources for distillation. Last but not least, how we can utilize knowledge distillation. Briefly, let me go over the definition of knowledge distillation. So there is a great large model, and with that teacher's model, we can train the students' models. That's what knowledge distillation is. The ultimate goal is to create better training signal. So I have prepared 3 images here. These are AI generated image. On the left-hand chart, the student is reading the book by himself. Next to it, there's a teacher face-to-face teaching the student. Last but not least, there are some implicit ideas the teachers have in her brain, and if that can be conveyed to the student, it will improve the efficiency of learning. So the technology that is matched to 3 areas would be label distilling, logic distilling, and feature distilling. So let me take a look at the label first. So that is generating the teacher model output and using that for training. Second, logic, it is to distill probability distribution at the token level. Compared to label distillation, this will deliver not just the next word, but the teacher model when it predicts what was the level of confidence with which it was predicted and what are the probability of other words being predicted. So it provides much richer information, therefore making the learning more effective. Last but not least, the feature-based distillation. This looks at the internal representation of the teacher model and distill that to the student model. For each layer, output representation or attention heads, attention map can be used for distillation. So let me compare these 3 areas. So there is a trade-off between effectiveness and efficiency. Label is simplest and most effective and efficient. It can create training all at the same time. Its implementation is very easy, but for logic and feature-based distillation, the student model and teacher model should have the same architecture. So there is a restraint for these models. So if we don't have to select one out of the 3. NVIDIA has announced Minitron, and after pruning the model, distribution can improve the pruned model's performance. And as you can see, embedding loss and encoder block output LM head, these 5 types of loss can be combined to train the model, and various combination can add other losses and improve the efficiency of the performance. As for loss function, usually the teachers and students output, there is the care divergence that needs to be minimized. Teacher models and teacher's probability can be the target, or students' number can be the target, and that will determine forward KLD or reverse KLD. There are various research about this. Some research says that forward is better. Other research says reverse KLD is better. In our case, we have tested this on our own. In general cases, forward KLD proved to have higher performance. So let me now talk about teacher model. Selecting the best teacher model is really critical for knowledge distillation. And if you only want to create small models, but you might need a large teacher model which requires a lot of resources for training. But logic distillation or feature level distillation requires teacher and students have same vocabulary and similar architecture, and the training data should also be similar to make the distillation most effective. So if the vocab is different between the models, can distillation be possible? Let me introduce you to related research. And you don't necessarily have to always go for the highest performing teacher models. Teacher model, when it creates the output, it can effectively do the inference based on certain technologies. This is when the vocabulary between model is different. This is about large distillation. Vocabulary is different, tokenized, and then sequence might be different, so logic level matching would be impossible. Sequence is different, and probability distribution is different, cannot be matched. In this research, tokenize must be done first to create different sequence and create chunks that can be aligned for two, and chunk can be created that aligns the two models, and there can be probability calculation at the chunk level, and with that divergence, training can be done. Even if the vocab is different, other additional signals can be extracted, which can be helpful. However, logic-based distillation is better, and it requires far less amount of information, so it's not going to perform as well as other models that have the same vocab. This is a similar research. This shows not the chunk level probability, but it looks at the teacher level probability and calculates the tokens. Compared to logic level models, this is less effective. Next, with the same vocab shared between teacher and student, when teacher has been trained and when student has been trained, when the distribution is different, distillation effectiveness can be low. And we did the test ourselves, and after distillation, student model used mixed languages or unlimited iteration. Hard label training models can sometimes be overconfident or underconfident. So compared to other training, it can do temperature calibration for distillation. And in selecting the teacher, computer optimal teacher must be selected. Distillation scaling law research shows that cross entropy loss of the student model and tokens quantity and teacher models cross entropy loss, it is defined as the function of these three. So when you plot that, you will get the graph on the right. This shows the amount of resource that you have, size of the student model, and the amount of training. And this can identify the expected loss. And you can come out with compute optimal teacher based on this data. One interesting here is on the left lower chart. It shows the teacher's loss is a denominator. This shows that teacher model's performance doesn't have to be the best to be most helpful. Teacher model's performance and student model's performance, when the gap exceeds certain level, then after distillation, the performance can be lowered And as you can see, the effectiveness can be degraded. In selecting the data, you can do it in a distillation effective manner. Mini PRM research shows that teacher models probability and its student models probability to define the characteristics of data for sampling. For example, teacher models probability is similar or larger than student model's number, then student model can follow the teacher model very well. So this can be a relatively easy data, so you can do downsampling for this kind of data. However, on the opposite case, teachers' probability and the students probably have a big gap, then students will not follow the teacher effectively. So you need to consider this as a diverse and complicated cases. So in that case, you might want to upsample the data to increase the effectiveness of learning. And for distillation, teacher model, student model, when they have a big distribution gap or performance gap, teacher models generated data can lower the efficiency of student model. But for on-policy distribution, distillation, it uses the data that student has created, and you put the logic from teacher model on top of that for training. We have actually tested this, and student models performance, if it's not high enough, then student models result itself will have low quality and did not have any advantage for performance. To apply this technology, it is important to make that students' performance achieve certain level, or you can do one sample, select one sample out of many. The best scenario here is teacher model and student model's output should be combined in the optimal manner. According to speculative KD, it got the idea from decoding. For areas that is relatively easy, we can follow student generation. When there is a big gap between the two, teacher models generation should be followed. So based on this approach, we have been able to combine and blend the student and teacher's label in an optimal way. We have done that, and this showed the highest level of performance, and teacher and student showed the highest similarities for distillation. Next, when multiple inference is done, since this is based on sampling, you could see that some output has low quality while others had higher quality. After multiple sampling, you can use reward model to select the best model, and with that data, training can be done to achieve the highest level of effectiveness. The biggest drawback here is compared to multiple sampling, relatively little data is actually used for training. Right-hand chart research shows that you don't have to always select top one. You could go for lower ones to improve the model's performance continuously. Here we have actually done the research ourselves and released that on ACL. When training on-device small models, we use a lot of knowledge distribution technology. Small models require multiple training. Sometimes hyperparameter learning is needed. And in this case, if we have to calculate logit separately, this requires just too much resources. So teacher model logit is inferenced and stored once, and we used offline distillation. The entire number of logit was too big, and we could not have all the storage to do that. To store one token, these days, models vocab is between 10 to 200,000, which requires huge amount of storage. So we cannot save all the tokens for all the logit. We did sampling, and Spot's offline distillation technology was used. So We did not go for the top angle. We followed the teacher's distillation and then looked at importance sampling-based sparse logits. So 12 out of 100,000 logits per token was good enough for us, and storage requirement was reduced by 3,000 times. Last but not least, I want to talk about how knowledge distillation can be used efficiently. I want to introduce you to some applications. The most important application would be to enhance the performance of the models itself, especially for smaller model performance. Gemma 2 and Quen 3, these are also used. We also have Gauss model for on-device and Gauss model for cloud. On-device model, we use the knowledge distribution on cloud-based Gauss models. As you can see on the right-hand chart, overall performance has been improved consistently. And after pruning the model, KD was used to improve the performance of the pruned model. Minitron model, after distillation, had model architecture change, therefore the performance could decline. So it's important to have the same level of output as the original model, and knowledge distillation can provide the additional training. And there are many cases when we have to inference, and speculative decoding is on the spotlight. Multi-token predictor or draft model training can also use knowledge distillation. For draft models, we need more than just high functions and performance. We need the original to have a similar distribution, and knowledge distribution can be very useful in this case. Conclusion: most of the model vendors might have the similar challenges. Knowledge distillation can be used for training variety of models, especially small models training. Recently, we are seeing agentic AI and related models are being launched in large numbers. They are also used for cloud and on-device. So on-device small models can sometimes have to be highly performing, and this will increase the demand for knowledge distillation. And knowledge distillation can be used to save cost. That is not wrong. However, based on our experience, for effective distillation, teacher models sometimes need to be built, and teacher model need to be inferenced for data retrieval, which is a very costly process. So knowledge distillation technology itself should not be used for cost saving. It can be used to maximize the performance of small models. So that is the end of my presentation. Thank you very much.